electroencephalography, which is commonly referred as EEG, is a very important biopotential signal. It tells you about the electrical activity of your brain. Currently, the EEG acquisition setups are very bulky. So if you're going with a normal EEG setup, you just have to use these electrodes and apply conductive pairs to these electrodes. So then you can establish a connection between the electrodes and the head. So it is very hard to do, and also people use this kind of EEG caps to capture EEG signals. So in these caps also there are a lot of electrodes, and you have to apply conductive pairs to each of these electrodes. Therefore, these bulky setups are limiting the applications of EEG. Because of that, the researchers are now moving forward towards collecting EEG signals through your ear. And most of the research are based on making earpieces that are specified for a special customer. As a research team from University of Moldova, we are proposing an earpiece that comes in 3 different sizes that could fit to a majority of the population. So this is our general earpiece, and we have the data collection unit of our earpiece. So this data collection unit will get EEG signal from your ear and will transmit those signals through Wi-Fi to your computer. And we have developed a user interface to directly interact with our device. Now let's move to the practical demonstration of our brain-computer interface. As you can see, there are 2 letters visible, Y for yes and N for no, but both letters are slightly dimmed and randomly one of them will light up. In this video, the person is focused on the letter N on the screen. So when the letter N lights up, the person's focus indicates they want to say no. We track and analyze their brain signals as the letters blink. By comparing the brain activity when Y blinks versus when N blinks, we observe a clear pattern. Our machine learning model detects these differences and confirms that the person is focusing on N, meaning the intended response is no. We utilize tiny silver chloride palette electrodes to comfortably and effectively capture EEG signals from within the air. These electrodes transmit the captured signals via coaxial cable to the PCB, where active shielding and filtering occur. Our design includes several filters to eliminate the noise in the hardware. Within the ADS1299 module, signals are amplified and converted from analog to digital. This conversion is key to our next step, which is digitizing the signals and then transmitting those to the computer. While we use Wi-Fi, a data cable is also an option. Once received, the signals undergo pre-processing, where we first apply 50 Hz notch filter to remove the power line noise, and then we focus on 1 to 30 Hz range, which is crucial for EEG analysis. Then, the artifacts are removed using some statistical methods introduced by us, refining the signals for the further analysis procedures. Our machine learning model, trained with transfer learning techniques, showcases our device as a brain-computer interface using a pre-trained brain-computer interface application and interpretable deep learning, where we ensure each decision is transparent and which is essential for medical applications.